So last time we saw that the group of units mod p was a cyclic group, and so we want to go on to study more general moduli. So it's natural to consider prime powers next. So mod p to the e. And as an overview of what we're going to do, we're going to show that for any odd prime power, the group of units mod p to the e is always a cyclic group again. In fact, item number 2, you can look at 2 times a prime power, and that again is a cyclic group. Now if p is an even prime, namely p equals 2, then as soon as the exponent is 3 or greater, we no longer get a cyclic group. The group of units mod 2 to the e is in fact a Cartesian product of a cyclic group of order 2 to the e minus 2 cross a cyclic group of order 2. So it's going to turn out that this will actually characterize the set of all cyclic groups, that together with 2 to the first power and 2 to the second power. So let's start with an odd prime power and show that for p to the e, the group of units is a cyclic group. So we start with GP. So we've seen that GP is a cyclic group, so let's let A be a primitive root mod P. So the order mod P of A is exactly P minus 1. Now it'd be really nice if this number A happened to be a primitive root mod P to the E. And it turns out that a lot of times it will be. There's an easy way to tell when the value A is going to be a primitive root mod P to the E power. So by Fermat's little theorem, by FLT, we know that A to the P minus 1 is congruent to 1 mod P, so it's of the form 1 plus Kp for some integer k. So I don't even need to know that the order of P. This would be true for any value A. A to the P minus 1 is of the form 1 plus Kp. Now, we're interested in whether P divides K or P doesn't divide K. So let's outline then what the strategy is. So we want to know, is A a primitive root mod higher powers of P? So here's our strategy that we're going to go through. First, if A happens to be a primitive root, where after doing the Fermat relationship, P is a divisor of K, then I claim I can replace A with A plus P, and I'll get another primitive root mod P because it's the same value mod P. But this time the K value right here is going to satisfy P does not divide this K prime value. And that's going to be a nice condition, because if I have, this is claim 2, if I have a primitive root where P is not a divisor of K, then for any n greater than or equal to 1, I claim that we're going to get a relationship of this type. And this will just follow by induction, that A to the P minus 1 raised to the P to the n minus 1 is of the form 1 plus some integer multiple of P to the n. And again, P is not going to be a divisor of the integer Kn. And it will follow from claim 2 that A is in fact a primitive root mod P to the E. So if you start with a primitive root, and the Fermat relationship right here has the property that P is not a divisor of K, then that value of A will continue to be a primitive root mod p to the e. So what does it take to show it's a primitive root? That means that the order mod p to the e of a is the Euler-Phi function, the number of elements in that group. And that's going to follow from claim 2, because here I've got an exponent which is the Euler-Phi function of p to the n, and that's going to give me a mechanism for proving this fact right here. So we'll do it in this order. We'll prove claim 1, claim 2, and then claim 3. Okay, so our first claim is that if I start with a primitive root where p is a divisor of k, right here, after writing down the Fermat relationship, then if I replace a with a plus p, I'll get another primitive root where p is no longer a divisor of this k value here. And that just follows from the binomial expansion. After all, what does a plus p to the p minus 1 power equal? That's a to the p minus 1 plus p minus 1 choose 1, which is just p minus 1, a to the p minus 2 times p plus p minus 1 choose 2, which is some integer, a to the p minus 3 times p squared, all the way down to p to the p minus 1 power. Okay, now where is the 1 following from? Well, a to the p minus 1 itself is 1 plus kp. So we got a 1 plus kp right there. And then I've got a to the p minus 2 times p squared minus a to the p minus 2 times p plus, and then all of these factors clearly have a p squared sitting as a factor. So let's just write p squared times some integer here. So I pull off the 1, which I see right in front, and then I pull off a p, and then I'm left with a k prime, where k prime is what? Okay, so I pulled off this p, so I still have a k right there. On this term here, I will have a p times a to the p minus 2, and then I will have a minus a to the p minus 2 plus a p times some integer. So I pulled off the 1. Every other term had a factor of p, and I just look what's left over. And then I claim that p is not a divisor of k prime. So what do I know? I know that p divides k. P is certainly a divisor of this term. P is certainly a divisor of this term. And p does not divide this term, right? Because a is a primitive root mod p, so p is not a divisor of a to the p minus 2. Therefore, p is not a divisor of k prime. It divides all 3 terms, but it does not divide this term right here. Next claim. Suppose now that we have a primitive root where p is not a divisor of k1. Then I claim that we have the following relationship, and that this is going to follow by induction. So proof by induction. On n. So when n equals 1, that's our hypothesis. So when n equals 1, is just saying that a to the p minus 1, and this would be p to the 0 power, is equal to 1 plus k1 P, and by assumption, P does not divide K1. So this is true by assumption. So suppose the statement is true for n. Suppose true for a given n. And now let's consider n plus 1. Okay, so I would take a to the p minus 1 raised to the p to the n power this time, and I have to calculate this. So that would be a to the p minus 1, p to the n minus 1 power raised to the pth power. By the induction assumption, which is our start equation, this is 1 plus kn p to the n raised to the pth power. And then by a binomial expansion, that's 1 plus p times kn p to the n plus p choose 2 kn p to the n squared plus dot 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 dot, and all of these have a very high power of p in them. They'll at least have a p to the 2n, which is more than we need, times some integer. In fact, I could have included this term as well. So, what am I trying to prove? I want to prove that this is of the form 1 plus some integer times p to the n plus 1, where p is not a divisor of that integer. So this is 1 plus p to the n minus n plus 1. I can see that here. Factor that off, and what am I left with? I've got a kn plus what? Well, this has p to the 2n in it, so you'll have the p choose 2, which has another factor of p in it. You've got a kn squared, and then I'll have a p to the n minus 1. The n minus 1 plus the n plus 1 gives me the p to the n squared, and then all of these will have at least a p to the n minus 1 power times some integer. And so, for n being at least 2, I want to claim that p is not a divisor of all of this. So p is a factor of this number, p divides this value, and p will divide this value also. Therefore, since p is not a divisor of kn, doesn't divide this value, divides these two values, therefore it does not divide this whole sum. So this would be 1 plus p to the n plus 1 k sub n plus 1, where p is not a divisor of k to the n plus 1. QED. So we've got the claim established. So that claim is going to imply that if we have a value a, having this property right here, with p not dividing k, then a is going to be a primitive root mod p to the e for any natural number e. So let's see. So we need to show that the order mod p to the e of a is the order of the group, which is the Euler-Phi function. So that's p to the e minus p to the e minus 1. Okay, so what do we know though? So by the claim 2, we've got that a to the p minus 1 raised to the p to the e minus 1 power, and that's the way you want to think of this. Think of this as p to the e minus 1 times p minus 1 right here, is congruent to 1 mod p to the e. In fact, that's just Euler's theorem. This is an a, this is phi of p to the e. That's congruent to 1 mod p to the e. But the other fact we get from claim 2 is that if you raise this to one lower power like this, this is not going to be congruent to 1 mod p to the e. And why is that? Since a to the p minus 1 raised to the p to the e minus 2 is an integer of the form 1 plus k times p. Let's write down. So what I'm doing is I am putting in e minus 1 right here. Like that. It's an integer of this form for some integer k. So this is by claim 2 here, with p not dividing k. So if the left-hand side here was congruent to 1 mod p to the e, then in fact you must have p being a divisor of k. So since p is not a divisor of k, that tells us that this relationship cannot hold. In fact, that this power of a is not congruent to 1 mod p to the e. Okay, let's let n denote the order mod p to the e of a. And so Euler's theorem, part 1 right here, tells us that n is a divisor of p minus 1, p to the e minus 1. Now, since a is a primitive root, mod p, and a to the n power is certainly congruent to 1 mod p, right? A to the n is congruent to 1 mod p to the e, because that's the order. So since it's a primitive root mod p, and a to the n is congruent to 1 mod p, then p minus 1 must be a divisor of n, because a has order p minus 1. So we've got p minus 1 divides n, and on the previous slide I said n is a divisor of p minus 1, p to the e minus 1 by Euler's theorem. So this putting together says this order is of the form p minus 1 times p to the j for some j less than or equal to e minus 1. But the second fact on the previous slide says that if I had one smaller power of p, I'm not going to get this congruent to 1 mod p to the e. This is fact number 2 right here. But a to the p minus 1, p to the e minus 2 is not congruent to 1 mod p to the e. Thus, the minimal power of j that would give us equal to 1 would be to let j equal e minus 1. We must have j equaling e minus 1, and therefore the value n, the order of a, is in fact the full order of the group. P minus 1 times P to the E minus 1. QED. Okay, now this slide I mentioned at the top, let's look at the group 2 times P to the E. And the second part of the theorem was to establish that this is also a cyclic group. And this will be immediate because G 2 times P to the E is isomorphic to G2 cross GP to the E. That was by the Chinese remainder theorem. And what's G2, the group of units mod 2? Well, that's just a trivial group. That's just the identity. And so this is just equal isomorphic to the group of units mod P to the E, which we know is a cyclic group, and so we are done. Okay, now let's turn to the group of units mod 2 to the E. So 2 is always a very special prime in number theory that is demanding its own special attention. So in some sense it's the oddest prime. Okay, and the claim here is that the group of units mod 2 to the E is cyclic only if E is 1 or 2. So as soon as E is 3 or greater, it's a Cartesian product of this cyclic group of order 2 generated by -1 times this cyclic group here, which will be of order 2 to the E minus 2. And it's generated by the residue class 5. So 5 will always serve as a generator for any power of E. Proof. Suppose that E is greater than or equal to 3. So the first step to proving the theorem is to show that the order of 5 in the group of units is 2 to the E minus 2 power. So it's not going to fill up the whole group. So recall the order of the group of units is the Euler-Phi function, which is 2 to the E minus 1 power. Half of the integers from 1 to 2 to the E are odd numbers, and those would be the units. So 5 is not going to fill up the whole group, but it's going to fill up half of this group. And it's going to follow from the following claim. 5 to the 2 to the n minus 2 power is of the form 1 plus kn times 2 to the n for some odd integer kn. So let's show how this claim establishes the fact that the order of 5 is 2 to the E minus 2. So first of all, letting n equal E gives us that 5 to the 2 to the E minus 2 power is congruent to 1 mod 2 to the E. So the order of 5 in our group is a divisor of 2 to the E minus 2. And I claim it can't be any proper divisor of 2 to the E minus 2 because, note, if I insert E minus 1 into this relationship, that's of the form 1 plus an odd number times 2 to the E minus 1. So this is not congruent to 1 mod 2 to the E. Because if it was, then 2 to the E must divide this difference, but that's a false statement by star with n equaling E minus 1. Therefore, the order must in fact be 2 to the E minus 2. Okay, so we have to turn to the claim, and I claim that the claim follows by induction. So let's prove by induction this result. When n equals 2, it should be straightforward. That's the base case. You'd have 5 to the first power well, that's just 1 plus 4, or 1 plus 1 times 2 squared. So K2 is 1, which is odd. So the statement is true when n equals 2. Suppose true for a given n. Suppose star is true for a given n, and consider n plus 1. So I just raise it one more time by saying this is 5, 2 to the n minus 2 squared, which is 1 plus kn 2 to the n squared. So it's 1 plus twice kn 2 to the n plus kn squared 2 to the 2n. And I want to write this of the form in star, so I pull off the 1. I pull off 2 to the n plus 1, and I'm left with kn plus kn squared 2 to the n minus 1 power. By assumption, kn is odd. This is an even number, so we have exactly what we want. An integer of this form with kn plus 1 odd, so 2 not dividing kn plus 1. Okay, now we're ready to complete the proof of the theorem. We claim that for e greater than or equal to 3, the group of units, mod 2 to the e, is just represented by the objects I have listed right here, the powers of 5 up to the order of 5, together with plus or minus signs in front of each one of those values. So I have listed 2 to the e minus 1 different values here, and that's the group order. So it suffices to show that the values I've listed in the parentheses really are distinct values, mod 2 to the e. So we know that the different powers of 5 are distinct because the order of 5 is 2 to the e minus 2. So the question is it possible for one of the positive values, powers of 5, to be congruent to a negative power of 5? So let's consider that down here. Can we have 5 to the j power congruent to minus 5 to the k power, mod 2 to the e, for some j less than k, between the listed values right here? Well, that would imply, in particular, that 5 to the j is congruent to minus 5 to the k mod 4, since e is at least 2 in size. E is in fact 3. And that would mean, while 5 is congruent to 1, that 1 is congruent to minus 1 mod 4. A contradiction. And so none of the positive powers are congruent to a negative power, so we really do have a full set of 2 to the e minus 1 distinct values, which fills up the group of units, mod 2 to the e. Okay, so we've established that g2 to the e then is just the direct product, where you look at the different powers of negative 1 together with the different powers of 5. So it's a Cartesian product. This is a cyclic group of order 2, and this is a cyclic group of order p, or 2, to the e minus 2 power. And I think I've set another item up here. In particular, the group of units mod 2 to the e is not a cyclic group because every element would have order at most 2 to the e minus 2. So 5 is an element of maximal order. Negative 1 has order 2. 5 has order 2 to the e minus 2. So no element would have order greater than 2 to the e minus 2 power. Now let's find a primitive root mod 625 as an example. So the strategy then is you start mod 5. So p is 5. And let's find primitive root mod 5 to start with. And that's easy. This you can just do by trial and error. Let's try the value 2. What's the order of 2? Well, the order mod 5 of 2. 2 squared is 4, which is negative 1. 2 cubed is 8. 2 to the 4th power is 16. So this is equal to 4, since 2 to the 4th is 1 mod 5, and 2 squared is not 1 mod 5. Therefore, 2 is a primitive root mod 5, and so we look at the Fermat relationship. What I've been calling the Fermat relation, where you take 2 to the p minus 1, and you want to write it as 1 plus some integer k times p, like this. So in our case, we've got 2 to the 4th power is 16, which is 1 plus 15, which is 1 plus 3 times 5. And so the k value is 3. And note that 5 is not a divisor of 3. And so by one of the claims we did in the proof, we know, therefore, thus 2 is a primitive root mod 5 to the e for every positive integer. So for all positive integers e. A remarkable fact. Once you have a primitive root mod the prime p, then as long as p is not a divisor of this k value, it will continue to be a primitive root mod every power. In particular, 625, that's just 5 to the 4th power. 2 would be a primitive root mod 625.